I'm back. This is the second video for electricity part 2, and what I wanted to show you is in reality what actually happens with electricity and electric potential versus the chart I've just drawn. So here we have a chart of joules versus various types of energy, and if we assume that at position A, let's make up a number, that we have 100 joules of potential energy. We have 0 joules of kinetic energy at A, because like the rock is not moving, or like the particle in the electric field, it's not moving. When we get to position B, it has 0 potential energy because it's lost its voltage in this case, or in the case of the rock, it is no longer has any height and it's all kinetic energy. But we will not get 100 joules back, and maybe let's just make it up. We'll say we're going to get 50 joules back, and the reason is that there are some non-conservative forces, friction, working in this case, and this is very obvious if you've ever plugged in your laptop or your phone and you put your hand on the charger, you will feel that it is warm. So some of this energy is dissipated in non-conservative forces, non-conservative such as heat, and that would add up to 50. And so this would be heat loss due to friction. Okay, so the law of conservation of electric charge is still true, or conservation of energy. 50 and 50 is still 100, but we don't get 100% kinetic because we lose some towards heat. And so we've already defined what a volt is, and a volt is the electric potential. You can have a high volt state and a low volt state, and it is the potential energy over the charge, okay, which for us is joules over coulombs. Okay, voltage with the AGE, this is the potential difference. And you've heard this, high voltage power lines. Don't touch the high voltage power lines because you're a low voltage thing and it will kill you. And potential difference would be the difference from state B, so the potential energy from B minus the initial potential energy divided by the charge, okay? And this still gives you joules per coulomb, okay? So you can have a high voltage state, a high voltage power line, which are shown outside there, or a low voltage state. And you'll note that when you change energy from one type to another, you've gained or lost energy, you've done work. So voltage is the work from B to A, which is also in joules, over the charge, again giving you joules per coulomb. Okay, as we said, electric current, we measure in amps. And amps, we use the word I. And this is physically how many electrons are flowing. How many electrons are flowing. Okay? And therefore, it's got to be charged per time. So 1 amp is going to be a charge of 1 coulomb over 1 second.
I didn't quite get that. Would you mind rephrasing?
Okay, ignore that. So electric current's an amp. I, how many electrons are flowing? Current is represented in amps, I or A, and it is 1 coulomb, which is the charge, over 1 second.